Good. So I'll also, the information about the final exam will be put tomorrow on the website. So once it's posted, I'll send you an announcement if you want to check it out. Again, I think in principle, we'll be done with the material for the course like on Thursday. And then if that goes as planned, then on Monday, we would just do like, review type problems or whatever. So let me start sharing. Our last class is Monday of next week. Yes. So we have 3 more classes, including this one. And again, the last one hopefully will be just more like review. Okay, so today, and obviously all of this is just for the final. Nothing that we're doing today is for today's exam. But so today, what we're going to do is finish 16.6 and actually do 8. So you'll notice that I'm skipping 16.7. We'll do 16.7 on Thursday, but it's just easier to explain 16.8. So you can sort of make them on the same lesson. So if you remember, there are like 3 main theorems on this course, actually. Green's theorem, more or less, we already discussed. And the generalization of Green's theorem can go in 2 different ways. And one way in which you can generalize it is called the Gauss's theorem or divergence theorem. And the other way you can generalize it is Stokes' theorem. So for today, we were going to talk about this generalization in terms of Gauss. So this is like what we're going to talk about today. So for that, we have to talk a little bit more about flux. I don't know if we discussed this very briefly. We didn't spend too much time about it doing this because it's sort of less important than work. But the idea was, I don't know if you remember the Raritan River. That if you're sort of, if you draw like a region on the XY plane, right? And you want to escape this region, right? So you wanted to escape this region. So in order to escape this region, like you are moving with some velocity vector, which for this, like in this case, we're just calling f, right? And so finally you reach the border or the frontier of this region, right? And so you're reaching it with some like velocity vector f, and the part of f, the component of f, which is responsible for you escaping the region, right, is the one that's like sort of parallel to the normal vector to the curve. So this curve like has like a normal vector, which I'm drawing here. Right, and the flux was just like the integral of of this normal vector. So if you thought of the curve as being given with as x of t, y of t, right? This is the curve. See, then the velocity vector was dx dt, dy dt, and the normal vector. I should put this like in capitalized, like. And then the normal vector was dy dt, x dt. And the flux, if you remember the formula for the flux, it was just like the integral of the dot product of f with the normal vector. So instead of it being with the velocity vector, which is the usual one that we use for work, for the flux, it was just the integral of f dot n. Okay. And t, whatever values it takes, like if it's like a closed curve, it's usually from 0 to 2 pi, but that's more or less how the flux was computed. Is that okay so far, so good? Any questions about this? Now the thing is like, okay, so the point is that if you live in a two-dimensional world, right, and you want to escape, I don't know if you ever watched this video about Flatland that I had posted on the Canvas site, but like there's a movie Flatland that you can find on Canvas where like the world is two-dimensional, right, and so all the creatures living there are like two-dimensional things like circles or triangles or squares. They're sort of like live in some weird social hierarchy in the movie because the circles are crazy. But if you are like, if you live in Flatland, like, right, you can only escape like rooms like are sort of two-dimensional like this. And so you can only escape through like they're like the door, like, you know, the doors are sort of like curves, right? Like you can only exit the room through like the boundary, which is in this case like a curve. But if you live in a three-dimensional world like us, right? If you are like in a room, like my room here, like if I want to escape this room, I have to go through like one of the walls, right? Meaning that I have to go through a surface, right? Because a wall is like a plane, right? So if you want to escape a 3D region, right, you have to go through like a surface. Is that making sense? In 3 dimensions. So imagine that, like, again, you had think of it as some sort of asteroid or like something floating in space, right? So you have like a
quick question to clarify something. The velocity vector f, that's pointing away from the paper or somewhere on the paper?
Oh, f is right. This is an illusion like of perspective. It looks a little bit like it wants to go like, you know, in the z-axis. I think that's what you're trying to say.
Got it. Okay. Got it.
And now it looks a little bit better. Yeah. Okay. Everything in this picture, everything is really on the plane, right? Like there are no z components, like kind of.
Got it.
Yeah.
But I was just thinking about the normal vector. That would be on the x and y plane.
Correct. Yes, because that's the thing. If you live in 2 dimensions, right? Really, you cannot see, like, there's like a normal vector which is perpendicular sort of to like the entire region, right? Which is we
okay. Oh, okay. I see.
But I'm actually thinking about the normal vector that's perpendicular to the curve, because that's the one that's perpendicular to your exit.
So say there was a tangent line on that curve somewhere, it would be the, okay, got it.
Right. Like for example, like this curve has like some tangent line, and then the normal vector would be the one that's perpendicular to that tangent line, right? Like everything is really here 2-dimensional, so you have never heard like the word three like z-axis, right? So if you have never heard about like the z-axis, like really the normal vector only refers to this vector which is perpendicular to the curve. Is that okay?
That makes sense. Thank you.
Sure. And then so, but like now, if you have some 3D region, right? If you're inside again, like something in space, 3D space, if you want to escape that, right? Like you have to exit, like you have to escape it through some sort of surface, right? So now here you have like some, well, let's try my drawing skills. So how does one draw like an airplane? Okay. Well, this is supposed to be an airplane. Okay. But so you were trapped inside the asteroid and then you have to escape it, right? So in order to escape it, like again, you are moving with some velocity, which I'm calling F. Think of it maybe as the force of the jet of the, you know, the engines or whatever. And so you get to this point, finally you're almost like you're here, right? But again, like the component of that's responsible for you exiting the surface is like the one that's sort of parallel to the normal vector. Is that making sense? So maybe I'll zoom it and stay here. So now the surface has a normal vector. Is it okay? Did I already scroll up or? So now the surface has a normal vector, right? So now n here is a vector normal to the surface. And so the flux through the surface will just be like the dot product. It's again like the same formula, but it's now the dot product of F with the normal vector. So
the F vector and the N vector have to have the same origin point, right?
you're sort of thinking of them as, right, like moving around in space. So
so they're dependent on the surface, depending on where we're
right, they're like,
surface.
they're strictly speaking like what people call like vector fields, meaning that you sort of imagine that there's one drawn at each point in space, you know, kind of. So like, right, you're not like, you know, before at the beginning of the class, we would always draw like the vector sort of at this, like with the same origin, right? Here is more convenient to sort of think of them like all over the place. So like the normal vector is really like when you compare them, like you're sort of comparing them at the same, when the two vectors, when they share the same origin, kind of. That's sort of what makes more sense in this case. So yeah, like they're copies of F, like maybe F is like doing something like this here, or maybe it's even pointing this way here and things like that. But yeah, like when you do the dot product, it's sort of like of the two at the same point. And then because there are many points on the surface, right? Like then you have to do like an integral if you want to have sort of like the total dot product, if that makes sense. So the flux in this case will be, right, it's going to be an integral because again, you sort of want to add up all the dot products that you found. So it's going to be the integral between F with N. And like just to say a little bit more of what's going to happen, it is like the idea, this is why we also talked about parametrizations. Like the idea is like for doing this flux, you actually parametrize the surface. So like let me just put it like this way for a second. You put like the parametrization of the surface here. So UV here like are the parameters that you use. I'm about to do an example, so don't worry about it. Yeah, the only difference is that this is a double integral, correct? Because like now the region of the escaping region is sort of two-dimensional. being a surface. And before it was one-dimensional because you could only escape through a curve. So that's like, okay. But that's essentially like the formula, but I'm about to write it in a way that's a little bit more convenient. So this is like the formula for the flux. Okay. But the thing is like, what you have to take advantage of is that if you had like a parametrization, you could find a normal vector to the surface. And I sort of mentioned this last week, but you may have forgotten already, but it's kind of useful. So if you had like a surface, let me draw it here, just like a random surface. Right. I don't know if you remember, like there would be, you get sort of like, you can sort of kind of draw like a grid on the surface. It's kind of like a curved grid. So you get like grids like this. And you would also get like things like that. This is sort of similar to the picture I did when I drew the adult Jacobian, when I told you about that. So if you look at a tiny piece of the surface, right, it's almost approximated by a tangent plane, right? And so the area, like, when we found the area of a plane or a parallelogram involves like the norm of a cross product, right? So if you want an actual vector that's perpendicular to the plane or to the parallelogram, you just take the cross product without taking its norm. So like what I'm trying to say is that here, like the normal vector can be taken to be this cross product that we used in the parametrizations. The one that you have been computing thus far, if you did like the examples about surface integrals, right? So like the only difference with what you have to do for today's exam is that for today's exam, you care about the norm of this vector. Now we are actually going to care about the vector itself, because this is going to be a vector that's perpendicular to the surface. Okay, is that making sense?
Can you explain that last part about the difference between the exam and this?
Oh, it's just that like, in the exam, when you're trying to find areas or things like that for surfaces, you take the norm of this vector, right? This was like the surface Jacobian, the norm of this vector.
Right.
Okay. So it's now we don't care about like just the norm, we care about the actual vector, right? Because now we need to use the actual vector in the dot product.
Got it. Okay.
So now we are actually working with the entire vector, not just with its norm. That's the difference. Is that making sense? So like the actual formula for the flux that you need to know, and this, like, I'm about to do an example. So so this is how you are going to compute in practice the flux. It will be an integral of f with the dot product okay. So this is a formula for the flux that you need to know. So let's do an example about this.
Do that because del R del U cross del R del V gives us the norm, and then it's magnified by whatever the f function is.
So it is the thing is like let me put it here, like if you had like two vectors, right? Like A and B, correct? Like the area of the parallelogram, right? This thing had area, right? Which was A cross B, correct? The normal
Yep.
of the, this is what in the previous problems, right? We were trying to find the area of like the surface, right? Which is why we only use the norm. But if you, this is actually why sometimes physicists call like cross product like some sort of area vector. But if you actually think of the cross product itself of these two vectors, right? You can think of it as a vector which is perpendicular to the plane or to this parallelogram and whose norm gives you the area, right? The thing is like now you do need the entire vector because you need to take a dot product, right? So you cannot just keep the magnitude because like the dot product only makes sense between vectors. So so that's more or less like what we're trying to do now. So the difference before was like for these questions about the like the area or things like that, or just integrating like a function over a surface, which we also did. I mean, like a function is like a scalar, so you can just multiply it by something like an area, which is also like a scalar. But where you're given a vector like a force, then you need to like dot it first with something, which is a vector. And so that's what we're trying to do. I don't know if that answered your question. So is that okay?
All good. Thank you.
Okay. So oops. So let's do let's do some examples so that you see in practice like in any case, like the idea of flux is heuristically telling you how much stuff is going through a surface. Like that's how you should think of flux. So because it has to do again like with this, whether or not you can escape something. So flux is kind of related to how much stuff passes through a surface. Okay. So let's do this example. So imagine that I give you this F, this formula for F. So F is going to be X minus Y, X plus Z. Oh, by the way, right, like maybe before going through that, let me stop sharing the screen. Go to Firefox for a second. So yeah, if you go to again like demonstrations project, I don't know if you have tried playing with it already. So you can go to demonstrations, Wolfram demonstrations, which is cute. And so you type flux, and there are some animations about flux. This is actually the same kind of flux that appears like in electromagnetism, like electric flux and other things like that. That's why this animation is called electric flux. But for some reason, this animation doesn't work very well from the app, but there are like some cute screenshots that you can see here. So, right, like the idea is that you have like a surface, like in this case, like this piece of paper, and you think of this flux like as a bunch of incoming particles. And so F is sort of giving you the velocity of these incoming particles. So you're like sort of looking at how many particles make it through the surface at like in some amount of time, and that's sort of more or less what the flux is computing. You see, and depending depending on what the angle is between the velocity of the incoming particles and the normal vector to the surface, like there will be more or less particles that manage to go through the surface. Okay, so that's what sort of this is trying to show you, that like depending on how you orient the normal vector, the surface, like the dot product changes, and so the flux would be a different thing. Here's like the formula. Okay, and there was another one which is kind of cute. Let's see. Oh, it's kind of the same idea. But you can like again like you just have to think of flux of how much like substance or material is passing through like a membrane in a given amount of time, kind of. That's what flux gives you. So let's say that this is like the vector F, and we want to know how much stuff goes through this vector. The surface will be the unit disk, but it's not going to be the unit disk, the usual one on the XY plane, but rather the one at height 1. So I'm going to draw the unit disk here. Okay, so
now we need to parameterize the surface now.
Correct. You always need to do that, right? So that's what we're going to start doing now. First, yeah, good. So let's try to find the flux. So right, like you have to give a parametrization of the unit disk, right? So what would be a useful like, and so usually here, like maybe I should write it first, like first always parameterize the surface. So let me put it like as a first step. Oh, and also like, let's see. Right. Usually, like I should have said this a bit earlier, but when you talk about a normal vector to a surface, right? Kind of like there are two options, right? Because if this is like a normal vector minus that is a normal vector, right? So usually normal vectors, like they can point like one way or the other, right? And this is kind of makes sense because if you're doing like a cross product, like you may have done like the cross product in a different order. So usually for the flux problems, you will be given like some sort of specification, okay? And so here, like if I am asking you to find the flux, what I really mean is that you choose, for example, the one where the normal vector having like say third positive entry or something like that. You'll see this in a second. So like I'm just saying that usually there are sort of two options for how you find the flux, because you have to say in which way the normal vector is pointing, okay? And so some convention needs to be made. And so in this case, like the convention for this example would be that you want the normal, like what I'm trying to say is that like the normal vector to the disk, right? Like the normal vector to the disk could be like this. Maybe this is like the most obvious case that you would think of, but strictly speaking, like the normal vector could also be this, right? So which one do you choose? And like you have to be told which one to choose. So it's not something like for you to decide, kind of. Is that okay? So there are like two choices of like, and you're told which one to use. So putting that aside, like how would you parameterize this surface or the disk? What's a useful parameterization? What would you use to parameterize the disk? Yeah, you can use polar. Good, excellent. Yes. So in polar coordinates, x becomes r cosine of theta, right? Y becomes r sine of theta, And what happens with Z? What can you replace that with in this case? Just one, right? Because yeah, exactly. The plane is like the disk is at constant height, right? So you have fixed Z to be 1, right? So the only difference of this parametrization versus like the parametrization of the disk on the XY plane is that here I'm putting 1 instead of like 0, right? So this is a parametrization in terms of like theta and R. So far, so good. So when you do the cross product, right? Sorry. Well, this one is not too bad to get because like there are zeros on this third column. So you get 0 for the first entry. You also get 0 for the second entry. And then in the last one, you get minus R sine square of theta. And then minus R cosine square of theta. And so you get 0, 0, negative R. So that's the cross product that you get here. So far, so good. Are there any questions about this? So what can you, so you should think of this vector that we got as being perpendicular to the disk, which kind of makes sense, right? Because it only has an entry on the third component, right? And so the only question is, did we find the correct one, right? Is this pointing the way we want it to point? Yes or no?
Yeah.
Well, what about the sign of the third entry, right?
Well,
so
we're given 2 choices, right? So we gotta.
Yeah, you have to. Well, in this case, the example was asking for you to choose the one where the that third entry is positive, right? So this is, I mean, it is fine. Like this is a normal vector. It's just not the one that we want in this example because this one has like negative third entry, right? So really the one that we should use in the cross product, like the one that we should use for the integral is like the one that needed to, the one where you would have done the cross product in the opposite order. So really the one that we should do, so we should have done and it's obviously not that you have to redo all of this because remember, if you just switch the order of a cross product, you just get minus the other one, right? Yeah, you just take it like you just take it with the positive R. Yes. Like what's happening here is like, I mean, you know, it's not obvious in which order, you know, it's not obvious in which order you do the cross product, right? Why should you have put like the partial with respect to theta first instead of like the partial with respect to R? So like that's like an ambiguity you cannot get rid of. So you are just like, you just decide to use like a convention. And so what this means is that if some of you had done the cross product in this way, by putting the partial derivative with respect to R first, then you would have been fine. You would just have found like the correct answer right away. But notice that like it's minus like, right, like there's an overall sign. So if this had been like 1, 2, like this becomes -1, -2, right? You have to flip all the entries. It's just that flipping 0, 0 is -0. So it's like doesn't affect anything, right? Well, usually for these problems, like it tends to be specified in terms of the third entry. Yeah. I mean, you could also have well, in this case, it wouldn't have made sense to specify it in terms of the first two entries, right? Because they're both 0. The specification is given to you, right? So you just have to make sure that you're just like complying with the requirements. But yeah, most of the times it will be given in terms of the third entry. So
a property of the cross product is the right hand rule, right? If you switch the order, then
right, exactly. Yes.
Okay.
Right, like so, yeah, like the third, right, all right. Like this is like a good example. So imagine that the plane had been like the surface had been like a plane that's parallel to the, to the what, like this is like the XC plane. Right, so if the plane had been parallel to the XC plane, then the normal vector really will have like just like an entry in the Y component. So in this case, you would have been told something like take the cross product that gives you like, a positive second entry. But there's some specification that's given to you. I'm just saying like most of the times it just works for the third entry. But yeah, there are like special cases like this one where maybe you say it in terms of the second entry or the first entry. Yeah.
Will there be an instance where, say, this given surface isn't like so perfect, it's not just parallel to one of the planes? What if it has like different Y values throughout the surface?
Like yeah, it's still like for example, like you could take like for example, if you take like a salad bowl, right? Like
yep.
Like in fact the normal vector is all over the place. It would be something like this.
Yep.
It just happens that depending of again, like how do you do it? Like here's like another way to like secretly, like this is like if you think of the salad bowl as, it depends on how you think about it, but if you think of this as x squared plus y squared minus z equals 0, the gradient of this level surface like would be 2x 2y minus 1, right? And actually this is sort of also like a normal vector. It's just that we're working with the parametrizations in this section of the course, right? But if you know the equation of the surface, like you could also find like a normal vector using the gradient thing. And so you see like in this case,
okay, makes sense.
Right, in this case, like it's true, like it's all like it is changing because like the normal vector depends on x and y, but in particular, like you'll see that like sort of like the third entry is sort of the same sign. So something always, and that it will or it can always be made to work, kind of. That's what I'm trying to say.
Got it. Thank you.
Yeah. In fact, like and actually like for like I'm about to say this in a couple of minutes. Really, like the surfaces that we really care about are the ones that are closed. And so by that I just mean like something like a sphere or like an egg, right? Or like a cube even. Although a cube really counts like as like a bunch of surfaces, one for each side. But imagine that you are thinking of it as like the like all of them together. Like when there are closed surfaces, that means that they sort of like, I mean, it's almost like by definition, right? Like they enclose something. So they're sort of containers, right? And if you think of them as containers, then like the convention is to choose the normal vector that points away from the container. So in this case, there's sort of like a standard convention where like you choose like the normal vectors that point away from the surface. Is that making sense?
Yeah.
These are called like the outwards normal vectors. So when the surface is closed,
Please, the spheres and ellipsoids are easier to calculate than the square, I'd assume.
Sorry.
I was saying the sphere would be easier to calculate than like a square.
Well, the thing is like yes and no.
Because
It's just that the
the
square
sphere
requires like 6 sides, right? So it's like doing it 6
Yeah.
sides, right? And so it's, I mean, it's more calculations, but if the square is sort of parallel to the axis, X, Y, Z planes, right? Like if it's not like a tilted square, right? If I give you like the square like nice, like parallel to the axis, then it's kind of easy to find the normal vectors. You sort of do it by visually, right? The sphere, like the sphere is kind of like, actually, like the normal vector for the sphere is like I'll probably write it at some point either today or on Thursday. It's kind of a mess. So, but it can be, yeah. Which will choose the normal vector that points away from the surface. So I mean, I'm just saying that there's like an obvious convention when the surface is close and closes something. But when it doesn't close up anything, then like you have to say something about which one you want to use. So yeah, so these were like some interesting asides, but it is an aside. So let me just write it here like it's an aside. So let's just going back to our problem. We had already found the parametrization. It was r cosine of theta, r sine of theta, comma 1. We already found the cross product that we care about, the correct one, which is 0, 0, r, right? And f, right? F was this thing. But now remember that again, for the flux and all these problems, like the idea is to rewrite x, y, and z in terms of the parameters. So this becomes like r cosine of theta minus r sine of theta, comma, no, let me write it downstairs because I need all the space. So f in terms of the parameters becomes like r cosine of theta minus r sine of theta, right? R cosine of theta plus 1, and then 1 minus r sine of theta. Is that making sense? So far, any questions so far, so good? So and then we're ready to do the flux. The flux is just the integral of f with this dot product. Okay. And in fact, theta goes from 0 to 2 pi, right? And because it's a disk, r goes from 0. It's a unit disk, r goes from 0 to 1. Is that so far so good? Are there any questions of the setup? In fact, and like, because again, this can be confusing. There's like I'm saying, like we're doing like sort of like an integral that has like polar coordinates, all right? So you might think, oh, shouldn't you just like put like an r in front of the r d theta? But remember that sort of like the cool thing about doing this cross product is that it kind of already has like hidden inside of it like the r factor, right? So the thing is like this vector does have like the r from polar coordinates, right? Like this vector has the Jacobian itself. So the Jacobian is sort of contained in the vector. So that's why you don't have to put like an r in front of the r d theta, because that's sort of counting it twice. Is that making sense? So like this is fine. Like, I mean, there's no need for like an extra r. The r is already baked into this computation of the cross product. Is that okay? So And so when you do the dot product, because this is a vector 0, 0, r, the only thing that survives, yeah, and also you don't need the magnitude in this particular example, right? Like you just need the vector itself. Yeah, you don't do anything with the magnitude in this problem, right? So since like only the third entry is non-zero, only the, like when you do the dot product, only the only thing that survives is like the third entries. So it would be like r, like it would be what, like 1 minus r sine of theta. That was the third entry of f, right? Because the other two entries of f like don't really work a lot, because like like this thing has the first two entries being 0. So in the dot product, the only thing that survives is this stuff. Is that making sense? Are there any questions about this? So really, like what you're doing is the integral from 0 to 2 pi, 0 to 1 of r minus r squared sine of theta, dr d theta, and that, I mean, that's not too bad to integrate. That should be pi. Is this okay? Any so far so good? Good. So this is how you find flux. All the problems about finding flux always require you to do this, so that's fine. And so now we come to like one of the big theorems. Like again, this is usually like this is the last theorem that is usually written down in all the multivariable courses. It just kind of makes it's a lot easier just to write it right after talking about flux. So the next big theorem of this course is like the divergence theorem, or also called the Gauss's theorem. And this is essentially all that section 16.8 says. So this is the divergence theorem. And what it says is really something very, very nice. It says the following: if you have again, if you have a surface in space, think something like this. So here now we have a closed surface again. So now we have a closed surface. And that just means that it encloses a 3D region. Let me call that region R. So here's a closed surface S. So S is a surface. And so let's call this region R inside the surface. So again, like the fact that it is closed, this means it encloses so think of this surface as some sort of container, kind of, or like a box, like right, like a box or container. like a closed box or container. Okay. Oh, good. Excellent analogy. Okay. Although here we're not trying to trap any creatures. So because it's closed, then it does make sense to talk about the normal vector that points away from the surface, right? So now this does make sense. So there's a normal vector to the surface that's pointing away from it. Oops, sorry. So here n points away from the surface. Okay. And if you have your favorite vector f, so let's call this vector, let's have another vector here. Let's say that this is where f is. F is doing its own thing. So maybe it's like here, or maybe it's here. So if you have f, which is a vector, so as a vector has 3 components, what the divergence theorem tells you, so what the divergence theorem says, is that the flux, right, the flux of f, which as we saw, if you want to compute it, you can, today's exam is 4 questions. If you want to compute it, it's just as this dot product. Right? What the theorem does is allow you, what it does is allow you to, instead of doing this integral directly, this double integral, you can do a triple integral instead. So what the theorem says is that you can replace doing this computation by something that's like a triple integral over the region R of something that's called the divergence, which is like, I'll say it, write it in a moment. Okay. And this will be called the divergence.
It goes from a surface to now we're doing it over this region R, which is the volume.
Right, it's like because it encloses something. The idea is that you can replace that instead of like for example, doing the I drew like some cases of closed surfaces here, right? Like instead of like if you had tried to find the flux over the sphere, right? That means like the flux over the surface of the Earth, right? What the divergence theorem is saying is that instead of doing like the integral over the surface of the Earth, you can do like an integral over like the crust, the mantle, like the core, like, you know, all the interior, all the inside. And what you integrate instead is something that's like this sum of partial derivatives, which is called the divergence of f. So this is called the divergence of f. Okay. So let me put it like, let me write it here. So divergence of f, which is like the other way, which is written is this way. And if you write it this way, it should remind you of like the notation we use for the curl, right? So you really should think here that you're doing like some sort of dot product. And what sort of the dot product is in this case? Well, it is like a dot product between the partial derivatives of an f1, f2, f3. So this is like the partial of f1 with respect to x, plus a partial of f2 with respect to y, plus a partial of f3 with respect to z. So essentially, you just take the partial of every entry with respect to its corresponding component. I mean, with respect to the corresponding variable in the alphabet. So first entry with respect to X, second entry with respect to Y, and third entry with respect to Z.
So then does the result of this give us the same thing, the same
It will give
outcome
you,
as we were getting before?
it does, yes.
Oh, okay.
And well, right, like the point is that it ain't obvious, right? Hence deserves the title of the theorem, right? Because it is saying that you can replace this double integral with a triple integral, right? So obviously, like that's not a clear statement at all. Like this is why, if you had proven it, it would probably have your name also, and not Gauss's name. So, but yeah, like it's like well, it's like, again, this is like why I'm saying this is like a version of Green's theorem, like an adult version of Green's theorem, because if you think of Green's theorem, what there were like really two forms of Green's theorem, but either form says that like you were trying to do like this integral, for example, of work or flux over a curve, but you can trade that off with a double integral, right? So all these theorems of what they're saying is that you can replace something like that is happening. You can think of the boundary, like the curve or the surface, as sort of like the end of your region. It's sort of like the frontier. So you can do like a trade-off where like the stuff that's happening at the border sort of can be replaced with something that's happening on the inside. Then they sort of give you the same answer. Okay. So let's see. Are there any questions? I'm about to do an example, so this will clarify it. So, but so far so good. Is this okay? Okay, let's do a cute example. Yeah, like at least let's show like seeing is believing. So let's just first like do it this way. So let's do an example. Let's take f to be x minus y, x plus z, z minus y. Okay. Now here's the thing. I'm going to take a surface, right? As the surface, I'm going to take the unit disk at height 1. Okay, so this is like, again, x squared plus y squared, that's really equal to 1 at height 1. Okay, but what's the issue with this surface, right? Like the issue is like the disk on its own, it's not like a container, right? Like the disk does not enclose anything, right? So if you want to find like the divergence, like if you want to make like something useful with the divergence theorem, you have to close it up. So how can you close it up? Well, you can think actually of like just drawing like a cone, like an ice cream cone, right? So now the disk together with this piece of the cone that does close up something, right? Which is this inside here.
Will this be given information, or do we have to kind of imagine it on?
No, like here, like the surface is usually given, right, all of it, yeah. So yes, you don't have to worry about that part. So the surface in this case would be like what I'm trying to say is like it's just like the surface is like the disk, right? Plus is the disk at height 1, oops, plus the cone, right? The cone Well, the cone, that's the part of the cone that's below the disk, right? Because, you know, strictly speaking, like the cone is sort of infinite in size, but you don't want, I don't know if you remember, like last time when I cut the cone, right? Like you don't want the full cone, you just take a part of it. So I'm just looking, like saying, like, just look at the stuff that's like below this plane so that it meets the disk. Is that okay so far so good? Is a picture, like, is the surface making sense? Yeah, good, excellent. Yes, exactly. Well, then sometimes they don't fill it up, so many times it's just empty, right? But so what the divergence theorem says, the divergence theorem says is that if you wanted to find the flux, it says that the flux of this surface, right, which is the disk plus cone, it's important to understand that it refers to the flux for both pieces, right? So what this is saying is that the flux of the disk plus the cone part, right? If you don't, sorry, someone was trying to say something, or if you don't want to do that, right, you can just do the triple integral over R, where R is like the inside of the ice cream cone, right? Of like this divergence of path. So here's where the theorem is being applied.
Does that mean that every time we need to find flux over a surface that isn't continuous, it would be like made up of multiple parts?
Well, right. If like strictly speaking, right, if you didn't know the divergence theorem, right, and actually I'm going to do something about this like in a moment. If you didn't know the divergence theorem and you wanted to find the flux directly from the definition for this thing, right, you sort of have to find the flux for the disk and then the flux for the cone and then add the answers, right? You sort of break it into subsurfaces, if that makes sense. It's sort of like, it's not that different from when, I don't know if you remember these work problems that tell you to find like the work for something along this curve, right? If
Makes sense.
you sort of break it for each line segment and add up the works. So flux can be added up, and I'm about to do it. So really, this flux refers to two fluxes, if that's okay. Yeah. But the one, like the one that we're getting from here is like I'll say it again in a moment, but it's like both of them. Yeah. But you'll notice that it's a lot easier just to do the triple integral in this case. So it's just like a triple integral. Again, like what is this divergence? Like you can think of this as making this dot product. So what do we get? Obviously, you can do this, like you don't have to be writing like every single time like the integrals. You can do first like the divergence to not repeat so many integrations. But so what you have to integrate here is just like the function 2 dB, the constant 2 dB. Because in this case, the divergence came out to be just like constant. Is that making sense? And good. So you're like, this is now this brings you back to the problems from the last exam, right? How would you do a triple integral for the function 2 or the constant 2 over this cone region? What would you do? How would you integrate the function 2 here?
Sorry, can you ask the question again?
Oh, sorry.
Can you ask the question again?
How would you do the integral, the triple integral of 2 over this region, over the conic inside inside of the cone? Yeah, you could use cylindrical coordinates, right? Like you can do the integral using cylindrical coordinates, right? So in cylindrical coordinates, dv becomes r dz dr d theta. Well, obviously, like the triple integral can be also done in spherical, or it could also be done in Cartesian, actually. But I mean, it is most of the times cylindrical tend to be a bit easier than sphericals. Yeah. So I mean, since you were not told which one to do, you could have chosen a different option, but it does become more cumbersome. So. What bounds should I use for theta? What bounds should I use for r? Zero to 1. And what bounds, this is more interesting. What bounds should I use for z? R to 1. Yeah. R to 1 because, right, if you draw the arrows, right? The cone is z equals r and so, right, they start at z equals r and they end at z equals 1. And let me draw this like this. Is that making sense? Like, are the bounds fine? In fact, you can do like a cross section if you remember cylindrical coordinates. Like you can draw the RZ plane if you prefer, and like what we're looking at is something like this. And so that's how you set it up. I mean, this is not too bad, right? This gives you 2 pi over 3. Is that okay? Now, so what does 2 pi over 3 equal? So this 2 pi over 3, you should think of it as the flux. Again, this is the flux of the system or the combined surface disk plus cone, right? So what really this says is that 2 pi over 3 is equals the flux of the disk, right? Plus flux of the cone, right? Is that making sense? Because the surface has 2 pieces, really. So really 2 pi over 3 corresponds to both of them, like the combined flux. Is that making sense? But now, I don't know. In fact, here's a thing that you can do. Like, I don't know if this seems similar, but this is actually the same F that I used in the previous example, right? This is the same F as before, and this was the same disk, right? So we do know already the flux through the disk, right? Anyone remembers like what the answer was from the last example? It was pi, right? So secretly, if you kind of sort of know that 2 pi over 3 then equals pi plus the flux of the cone. So in fact, like thanks to the divergence theorem and the fact that we had computed the flux through one of the pieces, we can sort of indirectly find the flux of the cone from this argument. So that tells you that the flux through the cone should be what? 2 pi over 3 minus pi. So it should be negative pi over 3. So that's one way sort of to not have like circumvent doing the calculation of the flux through the cone directly. Is that making sense?
Sorry, did the original question just ask for the flux through the cone?
Well, so right, like the original question, like the answer to the original question is 2 pi over 3, right? Because it asks for the combined thing, right? So I'm just showing this as an so this is like the answer, right? This is like the answer. Just this is like a more like a remark, right? That like this is sort of like an added benefit of like this, right? This calculation. That because because we had already found the flux through the disk, then you can sort of find the flux through the cone without much trouble. Is that making sense?
Yes.
In fact, like, and if you're a skeptic, right, what that means is that you should try to find the flux through the cone directly to confirm that you get minus pi over 3. So if you want to really check this, right, if you want to check this, how would you find the flux through the cone? You can find so what's the flux through the cone? Like, how would you find this from the definition? You have to find the parametrization of the cone, right? And what's the parametrization of the cone? Anyone, how would you parameterize the cone? Let me draw it here. What's the parametrization of the cone?
Is a cone without a top?
It's the cone without the top, right? It's now just like the conical part of the ice cream. That's a good, that's one parametrization, right? Excellent. That's one that works, but there's another one that also works. One could try. What's another one? In polar, right? So you get like r cosine of theta, r sine of theta, and then what do you get on the third entry? What should I put here? R, right? So this is another parameter. This is a parametrization of the cone, right? And so if you do this, right, you could find like the partial with respect to theta, like this is like parametrization in terms of theta and r. So you would find here minus r sine of theta, r cosine of theta, and then 1. Sorry, then 0. Oops. And if you find the partial with respect to r, you get cosine of theta, sine of theta, and then 1, right? So the cross product in this case What does the cross product will give you? Well, if you do it, let's see. Let me see if I find it correctly. In this case, the cross product that you find should be this one. Okay. So the flux through the cone would be the integral of, remember that f was like, what was f? X minus y, x plus z, z minus y dot this cross product. And what bounds do we put here for theta? Theta goes from 0 to 2 pi. And what are the bounds for the cone in R?
R.
The values for R go 0 to 1, right?
Right.
Yeah. So what that means is that if you do the integral from 0 to 2 pi, from 0 to 1 of, what is x? X, again, you have to look at the parametrization. So it's R cosine of theta minus R sine of theta, R cosine of theta plus R, in this case, R minus R sine of theta, dot R cosine of theta, R sine of theta minus R. So what I'm claiming yeah, is that if you do this dot product and you integrate this, you'll get minus pi over 3. So this is a challenge for you. You should check this. Well, I'm trying to do a wink emoji, but it doesn't work on the iPad. But you see, like, I wouldn't want to do this integral, right? Because just the dot product is kind of a mess. So I'm being told that the department website is not working. So I'll like post the announcement. I'll send a link. I'll post the solutions to the practice exams on our website in case you want to check them. But that's also probably I don't know why it's not working, but probably like next time also it's better to download them just to make sure it's in your computers. But yeah, I'll post them on the site. That's no worries. Okay. Okay, yeah, so good luck today. You can email me if you have any questions before the exam, and I'll see you on Thursday, and we'll do the last theorem of the class, which is Stokes' theorem. Okay, so yes. Well, I think the parametrization of surfaces is kind of complicated. Like it's what people get most tricked by. But yeah. So yeah, I can, if someone needs to ask questions, I can also stay here for. Well, I can change the deadlines again. I mean, they're not due. I mean, they're not really due today in the sense that, like, yeah, I can change them, but you could also have finished them before today. But yeah, I can. I have to check the deadlines. I thought I had already moved them so that they would not be today. But if not, I'll just move them again. Oh, your dog is there. Okay. Good. yeah, if someone has questions, let me know. Okay.